Okay, welcome to Let's Get to the Marks. Going through a question here on structure and bonding. Let's get into it. Define the term electronegativity. So, electronegativity, if we look, for instance, at this bond, the carbon chlorine bond, what happens? Well, you have a cloud of electrons here, and the chlorine atom is more electronegative and therefore has the ability to distort that cloud of electrons and withdraw it so that it is closer to the chlorine atom than it is to the carbon. At any 1 second, the electrons within that covalent bond are more likely to be closer to the chlorine atom than they are to the carbon. And so, yeah, that creates a polar bond. And how do we define that? We can say it is the ability of an atom to attract the pair of electrons within a covalent bond. Now, you could call, instead of saying a pair of electrons, you could say the electron density, um, or you could say the electron cloud around a covalent bond. So the ability of an atom to attract a pair of electrons, I think we could just say electron density. Some people use the term electron cloud. You'll have to check your mark scheme to see if electron cloud is allowed, but around a covalent bond. So the next question is explain why the carbon Cl bond is polar. And I kind of already went over that a little bit there. So the idea why the carbon Cl bond is polar is the chlorine atom has a higher electronegativity than the carbon atom. And the general rule for you when working out what atom is more electronegative is electronegative atoms that are electronegative are found on the right-hand side of the periodic table and up. So anything, if you imagine you have your periodic table, this is the crustiest drawing since humanity began of the periodic table, but you know it's got that kind of whatever shape. Okay, so anything on the right, electronegativity increases and going up here. So you're looking at the most electronegative atoms in the periodic table are up here, with fluorine being the most, followed by oxygen, which is in the group next door, or chlorine is just below fluorine. Chlorine's actually just also below oxygen, but it's still very electronegative. It's not electronegative enough to create hydrogen bonding, but it's still electronegative. You'll find fluorine, oxygen, and nitrogen are some of the most electronegative atoms in the periodic table, and they're found in the top right. So anything top right is very electronegative, and obviously opposite to that, these are electropositive, but we don't really use that term often in A level. So the chlorine atom has a higher electronegativity than the carbon atom. Um, so the chlorine atom um, draws the electron cloud or density, I should say, towards it. This makes so the electron density is not symmetrical, or it's unsymmetrical. Um, and what do I mean by that? I mean the cloud of electrons in the bond are withdrawn this way, making this delta negative and that delta positive. Now, I know I've already scored 2 marks there, but I would also include that. So I'd be like the Cl atom becomes, and it's kind of like that. Oh my days, what's that? That's like an alpha radiation symbol. What the? Okay, becomes that. And what do we want to say about the carbon? The carbon atom becomes delta positive or slightly positive, we can say. Yeah, there we go. Slightly negative, slightly positive. I always think of that as a weird S for like slightly negative, slightly positive. All right, let's just zing that on there. Okay, that is definitely all of the marks. Oh, didn't put myself a tick there. So you could, they like the term electron density, so the ability of an atom to attract the electron density of a covalent bond towards it, or the ability of an atom to attract the electrons in a covalent bond. It doesn't have to be pair of electrons because it could be pairs if it was a double bond or whatever. But yeah, that wouldn't happen with a double bond because they would be symmetrical in their electron density. Okay, anywho, enough whiffle waffle. Let's move on. Right. Ba, 3.3. Although the CCl bond is polar, CCl4 is a non-polar molecule. Explain why. So yeah, think about the bonding in CCl. It's going to be CCl4. You're going to kind of have a tetrahedral. The bond angles are all going to be the same. So although the carbon is still, although the individual bond is I'm still not talking properly. The individual bond here is still polar, but they're exactly 90 degrees apart or whatever they are. What is it? What's the tetrahedral? 109.5. They're 109.5 away from, they're all equal distances. And this means the electron cloud is evenly spread. And so the dipoles cancel out. So what we want to say is the bond angles are all the same. The electron cloud or electron density, I'm going to say the electron density is symmetrical, evenly spread. So the dipoles cancel out. It doesn't mean there aren't dipoles. There are dipoles, but they cancel out. So you get this situation which some students find confusing where CCl4 contains a polar bond, but it is non-polar. And so it has a polar bond, but all of those charges cancel out because it is a symmetrical molecule. So you could just say it's a symmetrical molecule. The dipoles cancel out, and that should get you the 2 marks, peeps. Right, let's zing on. There are van der Waals forces between non-polar molecules. Explain what causes these forces. So let's take a look at, say, a non-polar molecule. Oh my gosh, is that the best I can do? Oxygen, right? Let's take a look at oxygen. Um, why why do we get um, temporary dipole-dipole forces in oxygen? Well, at any 1 second, electrons are flipping. So at 1 second, the electrons might be in the bond, might be slightly closer to this oxygen. And then a second later, they might be slightly closer to that oxygen. And then a second later, they might be slightly closer to this oxygen, hence the bulge, no diddy, around this oxygen. And what this does is this means that temporarily that becomes delta negative and this oxygen atom becomes delta positive. And obviously one little oxygen molecule is not going to be on its lonesome. Okay, there's in 1 centimeter cubed, there's probably like a million oxygen molecules. So there'll be near enough another oxygen molecule close to it. And the repulsion of this negative, slightly negative oxygen atom will repel the electrons in this bond like that, because that is going to repel the electrons as far away from it as possible. And so this one becomes negative, this one becomes positive, and then what happens? That one's positive, so it's going to attract the electrons in this bond, because electrons are attracted to positive, so they're going to go down that end, and that one's going to become positive and negative. So the formation of a dipole here causes a dipole to form here, and we use the word induce. So we say formation of a dipole induces a dipole in this one, and then what happens is we get an attraction, which we show with a dotted line, a weak force of attraction set up between delta positive and delta negative, right? And that carries on like that. So that one's positive and this one is supposed to be negative. I should have drawn that there, but you get the ideas, peeps. So I just need to put that into words. So we're going to say the random, and so this is the first mark, the random movement of electrons causes one atom to be, yeah, delta negative. Could just say a dipole to form, couldn't I? But I'm being long. And the other to be delta positive. And then I could, if I want to get real poncy, in a covalent bond, causing a dipole in the covalent bond. So this causes a dipole in the covalent bond. That's that bit that's formed there. And then we need to talk. So that's the first mark, and I've longed it out. We could have just said random movement of electrons causes a dipole. And then this induces a dipole in the neighboring covalent bond for the second mark. This induces a dipole in neighboring covalent bond. Now, that was all that waffle I was giving to you about this delta negative one repels the electrons away from it in the covalent bond, causing this spark to become delta positive and this end to become delta negative. But you just solve all of that by just saying it induces the dipole in the neighboring bond. And then we say delta negative and delta positive between two molecules. There is a weak force of attraction. So a weak force of attraction forms between I'm going to write it this time, delta negative and delta positive between neighboring molecules. So what we're saying there, that is got to be distinct, is we're talking about the electrons within a bond here. The random movement of electrons causes a dipole to be formed. That induces another dipole, and that's the second mark, in the neighboring molecule. And then a force of attraction is created between the delta negative and delta positive between the adjacent molecules. Nice. And a final part to this question, barium reacts with oxygen to form barium oxide. Barium oxide has a high melting point and an ionic lattice structure similar to that of sodium chloride. Draw a 3D diagram to show how the particles are arranged in the barium oxide lattice. You should draw 8 particles, right? It says 3D, so I'm imagining if we check the mark scheme, you're not going to get, well, for a start, this isn't going to be 8 particles, but you're not going to get the marks for that. That is a 2D structure, folks. And that has got some big old gap there. So I don't know, it's not much of a lattice structure, is it? So that's a 2D structure. So you might say to yourself, oh, let me try and 3D this out like this. And this is where, I mean, I got equivalent to a level 4 in GCSE art or a D grade. So that's not great, is it? Look, my atom's not even fully a circle. So you might think, oh, can I do it like this? I'm not sure they'll accept this because this starts to get a bit difficult, doesn't it, to show. They want 8 circles. I mean, that looks kind of 3D, right? And they're alternative, but I'm struggling now with getting 8, aren't I? So it's much better to do this instead, which is like 2 plus. You could write BA 2 plus if you want. And then maybe I should label these BA 2 plus. Yeah, we probably yeah, I probably need to put the elemental symbol in there. So I'm showing off to the examiner. I know that barium's in group 2 and it's 2 plus. So this is a much easier one to do because you can clearly see the only misconnection with this is this appears, this is an ionic bond. And when you draw these straight black lines, it's kind of like signaling a covalent bond. Sometimes I find is what it looks like. And then that is probably the worst lattice structure in history. But yeah, oh my days. That would just about get me 2 marks. I think I might need to put the symbols in here, guys. So if you can do, I'm not going to paint it out for you, but if you can do, show the examiner that you know barium is 2 plus. And if you can do, show the examiner that you know barium oxygen is the 2 minus. So maybe I could just do it on one. Probably best to do it on all of them. Okay, that one I prefer because it's easier trying to do that. I don't know where I'd have to just continue it over here, maybe do 12 of them to show its 3D structure because you can't really see the ones that would be behind there. I could attempt to sort of draw them. I'm not sure the examiner would be happy about that. So yeah, I think this one here is the best way to show the lattice structure, if not the best ever drawing you've ever seen. All right, guys, don't forget sharing, caring, hit the like, punch up the bell, subscribe. Let's get to the mark, smash those exams.
You're still here? It's over.